What's up, guys? This video is going to be for finding the heat of vaporization of water. So right here I have some water that is just boiling. So it's at 100 degrees and it's just started to boil. And then I also have some cold water over here. And what I'm going to do is I'm going to take a small amount of this hot water, probably around 10 milliliters or so. And so I've got my balance zeroed. I'm going to weigh it on this balance. And so that should be fine. We've got 11.4 grams of water. So you got 11.4 grams of water at its boiling point. And then this container, I'm going to zero it and I'm going to put some cold water. So in this one, I'm going to put 179.3 grams of cold water. Now what I'm going to do is I'm going to take both of these. Actually, I got to find the initial temperature of the cold water. So the initial temperature of the cold water is almost there, sorry. It's 9.9 degrees. So we got 9.9 degrees for our cold water, and we had 179.3 grams of cold water. So what I'm going to do is I'm going to put these both on the hot plate. I'm going to turn the hot plate all the way up, and we're going to see how much energy it takes to evaporate this water that's already at the boiling point. So this water should start boiling pretty soon because it's at or near the boiling point. And we're going to see how much energy it takes to turn all of that to vapor. We're going to stop when this one completely gets used up, when it's completely all turned to vapor. Okay, yeah, it's already starting to boil a little bit, so that's good. And at the same time, we have this larger container of 9.9 degrees Celsius water. And we're going to see how much heat this one absorbs. The assumption we're making here is that these are both in the same kind of beaker on the same hot plate, so they're both absorbing the same amount of heat. And so by measuring this one, the temperature change, initial and final for this one, we can figure out, and we know the mass of this one, we can figure out how much heat this water absorbed, and we'll say that that's equal to the amount absorbed by this beaker. And so if we know how much was absorbed by this beaker to heat that water, we'll know how much heat was absorbed by that water to change it from a liquid to a vapor. Okay, and so we can see this one is boiling pretty well now. We got a good amount of vapor coming out of it. And so we're just going to keep heating this until this water is completely gone. This water is up to 18.9 degrees Celsius. 18.9 degrees Celsius. We know the specific heat of water. It's 4.18 joules per gram degree Celsius. And so with the equation Q is equal to delta T times mass times specific heat, we can figure out how much heat was absorbed by this water, and it'll be equal to the amount absorbed by this water, and that's how much heat it took to turn this one to a vapor. We know the mass of this hot water that we started with, and so we're going to turn that to moles because we want our heat of vaporization to be per mole. So once that's all gone, we'll be able to figure out how many moles of water evaporated, and by figuring out how much heat this absorbed, we'll know how much heat was required to turn that to a vapor as well. There's other ways to find the heat of vaporization. This one is kind of the simplest to set up, and that's why we're doing this one today. But there are other methods that could be used as well. But they all kind of rely on calorimetry, where you have some water that's releasing, absorbing heat, and you can figure out how much heat was released or absorbed by the water, and then set that equal to the amount required to turn the other water to vapor. All right, so it's boiling pretty well here. A lot of vapor is coming out, and so we're getting close to being done. And then the temperature of this water is continuing to increase. We're at 28.3 degrees right now, 28.3 degrees, and it's continuing to increase. All right, we're almost done. This water is just about gone. This water has gone up to 46.3 degrees. It takes quite a bit of energy for water to turn to vapor. That's why this is taking a long time. And that's why this much larger container of water has increased a pretty large number of degrees, because it takes a lot of energy to change water from a liquid to a vapor, or really to change any substance from a liquid to a vapor. The heat of vaporization is usually larger than the heat of fusion, because there's a big difference between a liquid and a gas, right? Liquids and solids are both condensed, so the particles are both pretty close together. But when you're turning this to a vapor, you're separating the particles completely, and so that's going to take quite a bit of energy. That's why this took a little bit of time, and that's why it's taking a significant amount of energy. Almost done. We just have a little bit on the bottom of that beaker, so we're getting very close to being done. All right, that looks pretty good. So this water is pretty much gone. And this water has increased to, let's see, 60.4 degrees is the temperature of this water. So we can figure out how much energy this water absorbed, and it's equal to the amount absorbed by this beaker. The energy that was absorbed by this beaker was going into a temperature change. The energy that was going into this beaker was used for a phase change. And since you know how many moles of water were originally in here, all those moles of water are now moles of vapor, are all vapor, and so we can figure out how much energy it took to turn that to vapor. That's it.